This is Programme 2 of VideoTel's series on practical marine electrical knowledge. The series is made up of 8 programmes. Programme 2 deals with the electrical distribution system on board ship, including its 3 main faults: earth fault, short circuit fault and open circuit fault, and their remedies. There are many system variations around, so it's most important that you become familiar with the components of the electrical system and the layout of the main switchboard immediately you join a ship. Pay particular attention to the layout of the emergency switchboard. This study will pay dividends during a blackout or when troubleshooting the cause of a major breakdown. Now, we must emphasize electrical safety. The golden rule is, before any work is done on an electrical installation, first isolate the circuit by removing the supply fuses or locking the circuit breaker in the open position so that the circuit cannot be energized accidentally. Then post a warning sign to alert others that the circuit is being worked on. Then prove the circuit dead with a voltmeter or an approved line tester. A switchboard can never be considered dead unless all AC generators connected to it are stopped, locked off, and all other supplies are disconnected. These points can never be emphasized strongly enough. The electrical rescue procedure is described in Programme 1 of this series. This is a typical radial AC distribution system. Its basic function is to provide electricity safely to all loads. It is a 3-phase, 3-wire, insulated neutral system, providing power at 440 volts and 60 Hertz. This is then stepped down by transformers to 220-volt or 110-volt single-phase supply and a 24-volt DC supply for some alarms, communication and emergency lighting. The ship's alternators supply power to the bus bars via main circuit breakers in the main switchboard. And from there, bulk power is distributed through feeder circuits and group starters to other load centers, section boards and distribution boards. Protection is provided by circuit breakers and starters with overcurrent and under voltage trips. Each branch circuit is further protected by fuses or miniature breakers. The alternators are further protected by instantaneous short circuit and time-delayed overcurrent trips. Reverse power relays and preferential load trips are also provided. Each circuit breaker or fuse in the system is designed to isolate a faulty or overloaded circuit from the system, which ensures the continuity of supply to all other healthy circuits. Whatever the design layout of your main switchboard may be, you'll have one panel for each alternator feeding the board and a synchronizing panel. Then there are feeder circuit breakers and group starter panels through which the supply is distributed. Many configurations are in use, and in most cases the controls for synchronizing alternators will be found on these panels, such as a voltage regulator, selector switch for manual or auto synchronizing, voltmeters, synchronizing lamps, the synchroscope, and frequency indicators. In addition, there will be speed governor controls for the prime movers and alternator circuit breaker closing and trip buttons. A detailed description of manual synchronizing is given in Programme 3, dealing with alternators. The output of the electrical system is then monitored by voltmeters and ammeters, kilowatt meters, and power factor meters, or kVAR meters. The health of the distribution system's insulation is monitored by earth fault indicators or lamps. The emergency switchboard is a smaller version of the main switchboard, but only the essential services are connected to it. The metering systems inside the switchboards are fed by voltage transformers and current transformers, which step down the circuit voltages and currents to safer levels for use in the instruments. Disconnecting a meter from a current transformer must only be done when the supply is off from the section monitored and the circuit is tested by a voltmeter to be safe. Remember to test the meter on a known supply before using it. Then the terminals of the current transformer must be shorted out. If this is not done, very high voltages will appear on the current transformer's terminals when the supply is switched on again. A most dangerous condition. This brings us to distribution faults. Earth fault first, as seen here. The insulation resistance of the entire system is monitored by an earth meter and earth fault lamps. When a fault appears, the feeder circuits and group starters are switched off one by one until the fault indication disappears on the board, checking first with the officer on watch that it is practical to do so. The fault will be on one of the load circuits being supplied by the circuit breaker last disconnected. Check all the individual starters on that group or circuit, again one by one, keeping in touch with the person checking the switchboard by a portable radio. An earth fault must be investigated promptly, because if another earth fault occurs on another phase, a short circuit fault will occur through the hull of the ship, tripping essential services. Even if this doesn't happen, the tracing of 2 or more earth faults on the same phase can mean isolating and testing each circuit individually in order to find the circuits involved. Once the actual outgoing circuit is found where the earth fault has occurred, its own circuit can be isolated at the distribution board. And a notice is posted on the isolator switch that the circuit is being worked on. The fuses are removed as an added safeguard. If motor heaters are fitted, remember their supply is usually separate from the main feeder circuit. They must also be isolated and tested. Back at the starter of the faulty circuit, another notice is posted. And the circuit is checked for being dead by a multimeter set to read AC volts. The test is between phases as well as between phases and earth. Then the feeder cables to the motor are checked by an insulation resistance tester for the presence of the fault. First, check the meter for correct function. Then check for 2 good earths. Then all 3 phases should be checked, even though the phase windings in the motor are electrically connected. By checking all 3 cables, finding the earth fault on all 3, you have checked against the possibility of an open circuit fault on that part of the circuit. Having found the earth fault on all 3 cable ends, the feeder cables must now be disconnected from the motor so that they can be tested separately, gradually eliminating the healthy parts of the circuit until the location of the earth fault is isolated and the fault found. The terminals must not be assumed to be dead, even though you yourself switched the supply off. Check that you have opened the right motor, the one which you have isolated. Check it with a voltmeter. A record of the connection of the feeder cables in the terminal box prior to disconnection will ensure correct reconnection after the investigation. This is important, as changing round any two leads of a three-phase supply to a motor changes the direction of rotation of that motor. The feeder cables have been disconnected. Now the terminals are checked to earth as well as the phase windings of the motor. The meter is checked first, then the test is made. This shows normal condition, no earth fault appears there. The feeder cables must now be examined. And here you are. A break in the insulation has caused the conductor to touch the casing of the terminal box. The fault is quickly remedied by cutting the cable where the insulation is damaged and stripping back the wire for a straight connector to be fitted on both ends. Alternatively, if the cable is long enough, cut off the damaged section and reconnect the cable to the terminal. Having completed the repair, check the joint for tightness. Reconnect the cables according to your sketch of the connection and check that the nuts are tight. Replace the terminal box cover. Back at the starter, recheck the circuit to confirm that the fault has been eliminated. The fuses can now be replaced and the isolator switched on.
Now we move on to open circuit faults, also illustrated here.
An open circuit fault causes the loss of a service, in this case a motor. The starter is withdrawn from the board, effectively disconnecting the supply from the motor. A warning sign is posted and the isolator switch is locked in the off position. At the back of the board, the feeder cables are now checked to find out why the service was isolated by the protection system. The connections here are good. First, each phase is checked for the presence of voltage, both between phases and between phases and earth. Then each phase is checked by an insulation resistance tester to earth, and then for open circuit. Although one phase has shown open circuit, you check all three phases. Remember, you always check for all possible faults. There may be more than one causing the breakdown. The open circuit can be a blown fuse or some other break in the circuit which would have activated the protective relay, causing the motor to be cut off from the supply.
Having checked the fuses, the motor terminal box is opened for examination. The fault may be in the windings, but more often it's found in the terminal box. Here you can immediately see that a connection has shaken loose. But before you do anything, check the terminals for being dead. Again, between phases and between phases and earth. Now the cable lug is cleaned and the connection is remade, making sure that the connection is clean and tight. Here, a lock nut secures the connection. Having checked that the fault has been eliminated, the service can be reinstated.
This brings us to our last distribution fault, which is a short circuit fault, shown on this drawing.
A tripped circuit breaker and blown fuses are usually the first signs that a short circuit fault has developed in a circuit. Do not reset the breaker or replace fuses before testing the circuit for electrical faults and the mechanical freedom of motor shafts. Check the circuit for voltage, then reset the multimeter to read resistance, or use an insulation resistance tester and check the circuit continuity at the load side of the circuit breaker or fuse. While investigating fuses and circuit breakers, it's important to remember that a single-phase supply on board ship is distributed on 2 live conductors and not, as on shore, by a live and a neutral conductor. Therefore, both conductors must be protected by fuses or breakers. First, check that the appliance is dead before working on it. When the fault is located, the damage must be evaluated. In this case, only a minor burn is found on the fitting, other than the damaged insulation on the conductor. Disconnect the damaged cable so that it may be removed. Clean the burned surface of the fitting. Cut off the damaged part of the cable and strip back the outer insulation, about 6 or 7 centimeters or 3 inches, to allow the cable to be reconnected. Then bare enough conductor to facilitate proper and secure electrical contact. A new cable must be used to replace the old if the damage is greater or if the length does not allow for safe reconnection. Now anchor the cable in place and then reconnect the 2 phases, ensuring tight connection. A loose connection will result in overheating and insulation deterioration, with further faults occurring. When the work is finished, the circuit must be checked again. If the test is satisfactory, New fuses of the correct size and type should be put into the circuit, or the circuit breaker can be reset.
This concludes the subject of Programme 2, dealing with the practical aspects of the distribution system. In this programme, we dealt with the method of safe distribution of the electrical supply on board ship, with all the safety systems built in. Next, we dealt with voltage transformers and current transformers. Then we traced and remedied an earth fault, an open circuit fault, and a short circuit fault. Special circuits within the distribution system, such as steering gear feed circuits and navigation lights feed circuits, are discussed in Programme 5.